Welcome. ShrinkWrap is a command in Rhino 8 that makes watertight meshes from open or closed geometry. As such, it is perfect to solve your assignment, where you in a previous segment have authored models consisting of separate surfaces with different colors. For 3D printing these objects, no color will be retained, so the different layers and different colors of the different surfaces are of no matter. But to create a 3D printable solid object from the end result of the previous assignment is a very gruesome matter if you do it manually. With ShrinkWrap, you can do it almost automatically. The caveat is that you get a mesh, and the density of the mesh might be excessive, and the file size of the exported STL too much for the slicing software to handle. So this tutorial will also cover how you in MeshLab reduce the complexity of the mesh. Both Rhino 8 and MeshLab are installed in CAD Lab in the computer room, so you are able to work with it there if you do not have access to Rhino 8 personally, like me. For specific help about ShrinkWrap as a command, you'll find the McNeil Rhino 8 documentation most sufficient. If you try to access ShrinkWrap from an earlier version than Rhino 8, you will see that there is no such command. So this tutorial was prepared in almost its entirety in CAD Lab when no microphone was present, so you'll have to bear with that the quality is subpar. Still, the tutorial's purpose is to help you complete this assignment in a more efficient way than manual modeling. Now let's start the tutorial. Import a Rhino file from the previous course segment into a new blank Rhino document. If there are missing fonts, ignore this. If there are missing textures or image files, remove these, since the 3D printed result will not be textured or colored. Enter the command ZE to zoom to extents. Change the viewport display mode to shaded to more properly see what surfaces there are. Select everything that is not a surface and delete this. If you for any reason have multiple copies of the geometry that you want to 3D print, evaluate which one you want to 3D print. Delete any superflouos geometry. Create a bounding box to easily move the objects from any bottom corner of the bounding box to the origin. To do this, you must first enable OSnap and also any relevant end snap point. Use M to move and 0 as the destination point. Find a suitable corner that you can rotate your object around so that you get a perfectly flat bottom surface. Without a flat bottom surface, the object will not adhere to the 3D printer's workbed. Use the command rotate 3D to rotate around first one axis and then the other edge of the corner to get a perfectly horizontal bottom. The command rotate 3D might seem a little finicky at first, but first you define with 2 points the rotational axis around which the object will rotate, and then you define the angle. If you have ortho snapping active, it will be easy because it snaps to 90-degree angle increments. With the model correctly rotated, let's make another bounding box to see the dimensions of it. This far exceeds the reasonable size to 3D print, so let's downsize this. Let's make a box with the length and width of 40 mm and the height of 60 mm. Let's select everything except the box that we recently created. Make a bounding box for reference for the scaling. Add the bounding box to the selection by shift-clicking and move its corner to the scaling box corner. Use the command scale to scale down the selected geometry down to the reference scaling box. If you find that the model still is too large with regards to any other axis, then repeat the scaling command for that axis as well. Delete both the scaling reference box and the original bounding box. Create yet another bounding box just to make sure that the dimensions are within the boundaries, 40 × 40 × 60. Ignoring the mesh on the right and creating a box that exceeds the width and the length of the model, Position this box so that you may use it as a splitting object, so as to make sure that the 3D printed model gets a completely flat bottom surface. With gumball active, it is easy to reposition this box so as to make adequate splitting geometry. With the move command, use V for vertical to lock the movement in the said vertical axis as a constraint. To verify that the vertical position of the splitting object is adequately placed, you may go to the front or right viewport and verify so. Select the adequately positioned box to be used as a splitting object and use the command trim to trim all of the surfaces which are at least partly below the top surface of the splitting box. In the perspective viewport, delete the splitting box and verify that everything looks as you intend, horizontal and flat on the bottom of the object. With the bottom flattened, make sure, with the bounding box yet again, that the bottom corner point is situated at the Z0. Move it, constrained to the vertical axis, to the origin. You may once again delete the bounding box. Ignoring the mesh on the left as well, select your objects and enter the command ShrinkWrap. You may enter the parameter values as you see them here, or experiment as you see fit. The ShrinkWrap command will take some time. Be patient. A minute or so later, this specific ShrinkWrap is complete. With the gumball, you may move it temporarily out of the origin so as to see it more properly, and you can change the display mode to Arctic. Instead of 100 non-printable separate surfaces, the shrink-wrapped mesh is one solid hull and can be 3D printable. However, at this stage, the mesh is very, very dense, and the high density together with a large file size may crash the slicing software. So there's good reason to try to reduce this in a separate software. We'll show this soon enough. As for now, if you are working in a separate document with your original geometry saved somewhere, you may delete everything else than the 3D printed object or the object to be 3D printed, make a bounding box and move it to the origin. Very good. Select the shrink wrap mesh and type the command export. Make sure to export as an STL file. Binary is best for the file size. It might take some time for the exporting of the mesh. With the model exported, navigate in File Explorer to where you exported the file and open the program MeshLab. If the file type STL is associated to MeshLab, then you may double-click the file itself. Otherwise, hit the Windows key and type MeshLab. You may keep the opening settings as default. Hit OK. You may orbit around the object by dragging the axis here. But the main thing that we're going to do is go to Filters, Remeshing, Simplification and Reconstruction, and then to Simplification, Quadric Edge Collapse Decimation. You may enter the parameter settings as you see here, or experiment as you see fit. The important thing here is that we want to reduce the file size for the STL so that the 3D printing slicing software does not crash when slicing. Hit apply when you are ready to initiate the remeshing. There will be a progress bar in the bottom center showing you how the progress goes. When the process is complete, you may click close to close the dialog window. You also see this in the log to the lower right that the filter has been applied. To save, go to File and export mesh as. So as not to overwrite the original file, you may choose any variation that you see fit. Use the default settings to save the file. When the file has been saved, you may navigate in File Explorer to your saved file. Make sure that you have Rhino active and click and drag the file into the Rhino viewport. Choose the option Import File. The default settings are fine. If we move the object with the gumball, we can more properly compare it with the original. And we see here that the density of the mesh is much less, but it also has one artifact. It says here that there are 2 meshes, so we'll need to find the stray separate mesh and delete this. Thus, we have now one mesh that is a simplified version of the original and is much more reasonable to 3D print without crashing the slicing software. We may verify that these are similar to the extent of being non-discernible if we go to the Arctic display mode and verify this. One always has to take into account the scale that you actually 3D print in. In this very small scale, details that may have been lost from the right mesh to the left mesh would still not have been visible. Delete the high density mesh, and with the bounding box make sure to move the low density mesh from a bottom corner to the origin. Delete the bounding box, select your objects and export. For the course delivery, make sure that the file name is as specified in a separate instruction. Binary is good. Click OK to export the object. As you see, the file size is much more reasonable than the original. As for the delivery of these files, as for this course context, it might be most manageable to simply go to home.ug.kth.sc, the KTH server, log in with your credentials if you are not logged in, go to Student Resources, Courses, Arch, and in here go to the specific course folder A21REA. In here you'll find a 2425 subfolder, and here you find a deliverables subfolder. In here you may, for the specific course context, upload the files. Please do consult any official course document before any of the information in this tutorial. This tutorial's purpose is only to make it easier to solve the assignment to create 3D printable objects within this course, but do rely more on the information from the actual examinator. This concludes this tutorial. Thank you for your time.